Assalamualaikum warahmatullahi wabarakatuh. My name is Irashka binti Musa. So today my group will present about the water level control system, and we are from the group 4 from section 1. Okay, so here is my group member. So the first student is Nur Akwanabila, and then the second one is Irashka, which is me, and then Asri Nur Hafiz and Muhammad Amirul Ashraf. Okay, so I will explain about the abstract. So the project is aimed to design and analyze the water level control system from the tank using PID controller, and then the water level control from the valve opening through the DC motor. So basically, we searching the system using the mathematically and simulation part, and then the output is the input is the water level HI, and then the output is HO, including the sensor that giving the value given by doctor, and then the sensor is for the feedback, and then we search for the P, PI, and PID controller. Then we compare it with the simulation in the MATLAB Simulate. And then we search for the overshoot, rise time, settling time, and steady state error. And then the result we need to demonstrate. We need to explain in the simulation and the calculation, the simulation and the calculation part.
Hello, my name is Asri Nur Hafiz bin Ahmad Shah. My metric number is CE230158 from Group 4, Section 1. And I'll be explaining the manual calculation for this water level control system. As you can see, there is parameters provided which consist of VA, JM, JL, BM, BL, KB, KA, RA, LA, GA, CD, H, and R. So the parameter has been given and we've put it into tables. Next is to derive the transfer function. So an equation for DC circuit is established, and as you can see, this is the equation: VA minus RAIA minus LAIA minus ES equals to 0. And we got the equation 2 and 3. Next, we substitute the equation 2 and 3 into the equation 1. Next is for the moment of the inertia and viscous friction is given. So we state the equation. Next, we convert it into frequency domain and substitute the equation 5 into equation 4, and we got the equation number 6. And we get the value of J and B. The value for J is the sum of JM and JL. We got 0.444 kilogram m square. As for the B is BM plus BL equals to 0.0035 ms radian power of -1. And lastly, we got the final equation for the transfer function, which is theta over VA equals to KA over LAJ S cube plus RAJ plus LAB S square plus KA KB plus RABS. And from this transfer function, for all the value we get, we substitute into the transfer function, and we got the transfer function equation is the final transfer function for the equation is theta ms over vns equals to 1.28 over 0.053724 s cube plus 4.973235 s square plus 1.6392 s. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Akwanabila binti Mak Fazil. My matrix number is DE220049. Now I would like to explain about our manual calculation. First, we have to find the mass balance from the equation, and next, we have to find the value of R So to find the value of R, we have to use the formula from the slide, which is the formula is km equal to ka over kb plus ka multiple with kb to find the value of km. Next, we have to find the value of tau. The formula of tau is rj divided by rb plus ka minus multiple with kb. So we have to do the sum equation and we will get the value of r. Value of r from the table is 2.08 second meter, and area of tank is 7.0686 meter square, and the height of water level is 1.25 meter. To find the tau, we have to use the formula, which is the value of area will be multiple with value of r, so we get the value of tau. The last one, we have to put the equation, the final equation, transfer function of the water tank level. We get the value is 0.7072 over 14.72 s plus 1. Next, we have to do the manual turning of PID gain. There is a table. The table shows the value of S, and then we have to find the value of A and also for B. For stable system, let A less than 0, and then we get the value of K. K is less than 118.4898. Next calculation is let B less than 0, and then we get K is more than 0. For the stable system, we will get the KCR equal to 180.4898. To find the value of S, we get the value of S is plus minus J 5.52238. The oscillation of limiting value of KCR equal to 5.52238 radian per second, and the oscillation, which is PCR, is 1.13776 second. The value K critical is 118.4898. Table 3 shows the formula to find the value of KP, TI, KI, TD, and KD for the controller that put at controller for P, PI, and PID. The table 4 shows the answer from the formula table 3. Those are the result using the second method of Ziegler-Nichols that's shown below. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. So today I will explain about the open loop block diagram. So I will ask you to I will explain to you about the open loop block diagram. So here the first step is I already put this because we need to move faster. So we click the library browser to get the parameter that we want. So as you can see, the first is we need to have the step. So it's loading a bit, and then we find step. So here is the step. Okay, and then it's loading a bit. And then the step will pop up there. Okay, here. And then this is the gain. Okay, so we edit a bit. Maybe it's lagging somewhere. Okay, and then what else? Okay, we need to find the scope. drag scope here, close the library, then the scope here. Okay, and then we, oh sorry, okay, double click here to generate the output. So we need to output tools. I don't remember the tools or files. Oh yes, number of input output. Change to 2. So here is they have 2 part. So here is the system sensor, and then we put the transfer function for the DC motor. Here we put the exactly the one, and then for here is transfer function for water tank level. So click here. We need, okay, so the numerator pipe, okay, is 0.07696, and then the numerator pipe was S is 0.01. So then click apply, then okay. Then here, then we connected. So here with the game, with transfer function to water level function, and then move a bit. Okay, so there, here, and then this part, okay, we drag it to beef sensor. Okay, so I think it's done. So we run the simulation. Okay, then we click on the scope. So here is the graph for the open loop. To change the simulation, okay, so I think that's for the open loop.
Hi, Assalamualaikum. My name is Muhammad Amir Ashraf bin Kamrul Zaman. Today I would like to present about the implement PID controller. So this one is our fully circuit. So this one I just set up the circuit because I don't want to take time. So we just search gain to set up the PID controller, and then this one DC motor and water tank transfer function. So for the transfer function, we just right click and then search the transfer function. So we get the block of the transfer function and just put the our transfer function, and then we just search scope, step, and then this one is summing for PID controller, and then we just set up the circuit like this. uh, Also for the setting for PID, we already get from the manual calculation. So as shown in this table, we just put the value in our gain at PID controller. So for P 0.0273, for P is 0.0246, and then for the I we get 0.0003, and then for the PID controller, for P we input the value 0.03276, and then for the PI we just put the value 0.0006, and then last but not least for D we put the value 0.4483. So we just run this block diagram to see the result. So we open the scope, This one is comparison between three response. So as you can see, the blue color is P controller response, the red color PI controller response, and then the purple is PID controller response. So that's all for me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So today I will explain about how we get the result for the auto-tune block diagram. So today I will explain and I will show you how we get the output. So firstly, so we design this output, this block diagram. Okay, here is the block diagram. So I already put the transfer function and water tank for the sensor, step and scope. So today, so now I will search for the parameter sum. Okay, search it. Okay, so here's the sum. And then we change the parameter to positive and negative. Then apply. Click OK. And then what else? Oh, the PID. So PID. Okay, PID controller. So put it here. Okay, it maybe takes time. Okay. So we arrange. And then we connect the circuit. See. And then the gain, see here. Sensor. Same as previously, how do we put the value? Just click this transformation and then put the value here. Apply, then OK. Same as the water tank. Click, then OK. Apply, then OK. So again, we put for the scope. Okay, so then, so we need to put the VID value. Okay, PID value, we back to the report. Then, sorry. Okay. Okay, so for the P, we put 0.03276. And then for the I, 0.0006. And then D, 0.4483. So this is from the manual part. This is 100. Apply. Then let me, I can show you. Take from this part. Right, and then we after we add it, we'll get the automatic part. We tune. Maybe it's take time. Okay. So they will generate the obtain the plan model. Okay, so it will generate the PID to result. Okay, so here is the result. Okay, click option, the first output, first graph, click balance, then update log. Okay, so here is the, okay, then we click option, reference tracking. So it's have the slightly different. the block and the tune response. So we click to show parameters. So it pop out this bar. Okay, we have this like different here. So we put this value into here. And then set the parameter, the rise time, settling time, overshoot peak, gain margin, phase margin, the closed loop stability. Both it's stable, so it's good. So the block diagram is good. So here is the PI and PID for the new tune. We move. So if we click back at the PID, so here we'll pop out the new PID. Okay, so I think that's all for me. Thank you.
In conclusion, our research highlights the PID control algorithm as a widely used, reliable, and adaptable technique, particularly effective for controlling DC motor speed. Its combination of proportional, integral, and derivative components enables precise control by addressing rising time, steady-state error, and transient response. Through MATLAB simulation, we successfully designed and analyzed a DC motor system demonstrating the practical implementation of PID controllers in industrial and automation application. Furthermore, this study emphasized the importance of both traditional and modern control systems in advising sustainable technology development. Thank you.